Okay, hopefully people are up and running. Can anybody jump in and say that they're there?
We're here.
Yep.
Okay, so sorry I'm a little bit slow getting started. And then I'm having some pen calibration issues. So it will take me just another minute, and I think I should be in good shape. Okay. Okay. I kind of forgot that I had already started this lecture 3. So I think we will definitely get through lecture 3, these PowerPoint slides for lecture 3, and we might end up ending a little bit early. So we'll have to see. Okay, so one comment is this second homework set. Did anyone get an email, some notification from Gradescope?
I did.
You did. Okay. So I guess I'm going to switch it around and do the other direction then. If you didn't see anything from Gradescope, maybe send me an email to let me know. I think I wrote an email explaining a reason that Gradescope might make it easier for me to grade homework. So hopefully once you get the hang of how you put things in Gradescope, it's not a huge difference between Gradescope and Blackboard, and maybe makes it a little bit more like grading paper homework because I can get right to a certain problem. So we'll try it out. And again, if you have problems when it comes time to putting it in Gradescope, don't get all freaked out. I know I'm quite particular about things being turned in on time, but let me know if you have a problem. You can send it to me through email, and we'll get things worked out, hopefully eventually. Okay. Just before class, I looked and I saw most of you had done your first review paper, so that's good. And I've posted your second homework, and you guys would be ready to do that second homework already. So even this content on thermal resistance is not on that homework set. So you are ready to do all those problems. So we started thermal resistance last time. I've got my notes here about the things that need to be true in order to use the thermal resistance network idea. This is a table that we talked about the other day. I think it has a few useful pieces on it, but right now the part that we were maybe hitting towards is what the thermal resistance element looks like in these three typical geometries that we look at. And maybe, yeah, they've got it down here. They're making it clear that this is a thermal resistance for conduction. So we're thinking about conduction through a wall or through a chunk of a cylinder. So a cylindrical wall, we got radial conduction, or in a spherical shell, we could also have radial conduction and have a thermal resistance element. Okay. We maybe introduce this idea that there's an analog to electrical systems, that we have what flows is current, and it's a change in voltage over an electrical resistance. And for us, what flows is heat transfer, And we've got what drives it is that we have a temperature difference, and the analogy is a thermal resistance element. And then if you remembered your electrical circuits class, how you can put resistors in series or in parallel, we can do those same things with thermal resistance elements. So we talked about putting them in series or in parallel. Because this thermal resistance idea is kind of powerful, it would be nice to be able to extend it to convection and radiation heat transfer. And again, you guys have seen this before, so maybe I should be going a little bit faster. But for convection, for example, that's Newton's law of cooling. That's our general equation to describe convection. And if I wanted to put this in my typical form, delta T over thermal resistance, well, here's my delta T. So it says thermal resistance is 1 over a convective heat transfer coefficient times area. And just a reminder, so we have a lot of areas that end up appearing in these equations. This is a surface area, because you're thinking about if I have convection from a cylinder, it's the surface area of the cylinder, not because I'm driving my temperature differences. I got some temperature in here, I got some different temperature here, driving the heat transfer. It's through the surface area. It's not a cross-sectional area. So I've written down Stefan Boltzmann equation for describing heat transfer due to radiation, by radiation. Okay, and if we want to do this same thing again, we're trying to figure out how could I write a resistance element for radiation. If I expand out this temperature difference, okay, well, there's my delta T. So the thermal resistance element looks like everything else in this equation. All right, and I'm going to put the A at the end. So I'm just doing a little bit of rearrangement. Again, that would be a surface area. So one more thing that we might do, and this is thinking back to what the convection looks like. It's a 1 over a heat transfer coefficient and surface area. Well, sometimes they'll talk about this combination is an effective radiation heat transfer coefficient. Okay. And you're thinking it should have the same units as a heat transfer coefficient for convection. So watts per meter squared Kelvin. And then I could write this as 1 over HRA. I'll put the surface in. Anyway, it gives some, I don't know, similarity between writing the convection and the radiation resistance elements, although the radiation has more complexity associated with it. Okay. Rather than having to do all of these, TS squared plus T surrounding squared, there is an approximation to estimate the effective radiative heat transfer coefficient. And it's valid when T surface to T minus T surroundings isn't too large. And I'm only going to leave it as too large. You got to look at what kind of error you're willing to accept. Okay. And you can calculate and see what kind of error you are incurring. But the approximation is that we're going to define this average of the surface plus surroundings. Okay. And that this estimate just involves an average of the surface and surroundings. Okay, so then you're thinking, well, if I knew surface and surroundings to take the average, well, what benefit is this simplification? And let's say you don't know one of them. You don't know the surroundings or you know the surface, but you have this idea that they're close together. Well, the approximation you're going to use is just use T surface over or T surroundings in that equation to get you at least close, to give you an approximation for this radiation heat transfer coefficient. Maybe it's really small and you can say, I don't even need to consider it, or maybe it's on the same order as convection. It at least gives you a starting place rather than having to deal with, let's say, surface temperature up here is unknown, and you're carrying this unknown to the third power around.
So I know you mentioned that it's really dependent, but are we like grand scale? Are we talking within 10 degrees, 15, 30 decimals of degrees? I'm not sure.
Yes. Okay. So, and I put a little, chart in my notes, and I have have the students do a homework set on this, and we'll see if I did this. But so let's say I have TS 400 and T surroundings is 300. Okay, so 300 you would think is kind of standard temperature of the walls in my office or a building. Okay. Okay. And my error, if I calculate HR using, T surface and T surroundings versus using this, the average of these two, my error is 2%. When I get up to, if I did 600 and 300, and that is Kelvin. My error is about 10%. Okay, so within 100, I think we're doing pretty good. By 300, maybe not so good. Okay. We are going to see, well, hopefully I will make that point when we get to a problem, that there can be cases we don't know the surface temperature. To me, that's often a situation. We maybe know the surroundings, and we'll just use this approximation to at least get our problem started, to get an estimate of what the radiation heat transfer is. And we can go back and fine tune once we get the model in place. Okay. Okay, so we have this idea that we can combine any of these thermal resistance elements now. We can put together convection and conduction and radiation thermal resistance elements. This slide is to introduce this idea of contact resistance. And if I was going to draw my big picture to show what contact resistance is that I have slabs of material. This is going to be material A. And this is material B. And usually I draw these straight lines, but I want to enhance this idea that on a fine level, if we zoomed in, that these materials don't make perfect thermal contact. Okay, just for curiosity's sake, can you guys hear that I just turned my air conditioning in my office back on?
I did when it started up, but
not
yeah,
really.
but
not now.
Yeah, we can't hear it.
Okay, okay. All right, so these two materials don't make perfect thermal contact. So there's what's called a thermal contact resistance to them. So let's say material A is hotter, and I'm going to draw a temperature distribution. So let's make T through here. So this is temperature, and I'm moving through these materials. And I should make this a little bit taller so I don't run out of space. But let's say, so the temperature distribution looks like this through this material A. It's dropping off. I've got heat moving in this direction. Okay. And then when I get to this thermal resistance element, I'm going to have a little drop. Okay, and I'm making it look bigger than it really might be, but just to show something. And then maybe in material B, now it moves off. It's got some different thermal conductivity, so its temperature is dropping off at a different rate. But through that little resistance element, that there is some resistance associated with that gap, and it causes a temperature drop. Still same Q going through this whole slab of material, though. Okay, the notation our book uses is R, and there's a little T, and I've been using TH, I guess, to be a thermal, but they will just use a T. Hopefully that will throw you off. Thermal, C is for contact resistance. The double prime has a meaning. I always think it's a little bit backwards when I think about it. So its units would be thermal contact resistance has units of meter squared Kelvin per watt. And just a little aside, we haven't looked at this before. You're going to do more problems and feel more used to this. But let's say, just to be thinking about units. So this is my little scrap paper over here. Let's say R thermal. And I'm going to do conduction through a wall, because this is an easy one to do. L over Ka. Okay. And if I was looking at units, I would say length has a unit of meter, and K has units of watt per meter Kelvin, and area is meter squared. So if I reduce this, I have units of Kelvin per watt. Okay. And that is typical units for a thermal resistance element. Okay. Okay. So the fact that they put this double prime in here for contact resistance, that should give you a hint that there's an area to deal with. But to me, usually the double prime means per unit area, and you can see that the area is in the numerator. So I would say just remind yourself, watch units. So most often how you're going to use this to get back to this kind of unit is you're going to divide through by area. So and that gets you back to standard thermal resistance units. Tables 3.1 and 3.2 give some thermal contact resistances for some materials. And I'm going to tell you, it's almost always metals, and there's a reason that's what it is. Okay, so this is an example. This is for two copper slabs put together, and there is a vacuum between them. So there's not air in that gap. There's not a fluid in the gap. There is a vacuum at that surface, that mating surface. So this case for copper with a vacuum between the thermal contact resistance 1 times 10 to the minus 4 meters squared Kelvin per watt. So these are pretty small thermal resistance values. Okay. I think we're ready to go back up and look at this figure. That was kind of the dominant thing on this page. Okay. So first thing on this page is that this axis, on the y-axis, is showing 1 over contact resistance, which is like a conductance. So instead of, we've taken the flip, so we're saying instead of how do I resist heat transfer, I'm saying how well do I conduct heat through this, this little gap. Okay, and they've even written this out. So they've got 1 over, oops, sorry about that, 1 over area times the thermal contact resistance. And if I was writing it in our book's notation, it would be 1 over R T C double prime. So just think it's the reverse of these, of a thermal resistance element. And then on this axis, they have got clamping pressure. Okay. So they're looking at a few different features in this graph. So they're looking at this thermal contact resistance, but as a function of, for example, they have it plotted as a function of clamping Okay. And if you can picture, you know, I have these 2 chunks of material, and whether I'm pushing them together more forcefully or less forcefully, I think the idea that as pressure increases, you can see the conductance increases. Or you think of it as the resistance is decreasing, and that kind of makes sense. You're pushing it together. Some other things on this chart, and it's maybe kind of small for you to see very well. Hopefully you can see this if you can zoom in, is it also has, it's got this delta squared to the 1/2. That's root mean square of the roughness of these surfaces. And you have to look through the data that's given, but that, I hope you can imagine that that would be a factor that would have some importance. If I have big roughness elements and I put these 2 together versus I have pretty smooth and I put them together, have them sitting right next to each other. So more surface roughness, I'm going to have a larger thermal resistance, and I'm going to have smaller conductance. Okay. Another factor in this is looking at the hardness of the material. Okay. So depending on which materials, copper I think of as being relatively soft, stainless steel not so soft. So as you, again, put these 2 surfaces together, the softer they are, some of these bumps might smooth out and make a better thermal contact. A fourth thing that it has as a specified is what is in the gap. And this is really tiny, but hopefully you can see. So that says vacuum, and this says air in the gap. and maybe those are the only options in this table. But whether I have a vacuum, so you think if I have this gap and there's nothing in there, my thermal contact resistance is going to be lower. Everything has to be by radiation, as opposed to if I've got air in there, I can rely on the air as a pathway to move heat from one material to another. If you put a fluid, so if you had water in the gap, you would have a smaller resistance and higher conductance. And then if you put thermally conductive paste, that's going to give you a even better pathway for conducting heat across this surface that's not perfectly machined. Okay, I like this chart just because it gave some things to think about relative to contact resistance. Maybe the last thing I want to talk about before we leave this is why, if you looked at this chart, it's always showing like copper and copper, stainless steel to aluminum. Why are those the materials that we see contact resistance for? If I had two metals put together, and it's been a while since we talked about this, but metals have really high thermal conductivity. So they're really low resistance. So I could have a slab of copper, really low resistance, a slab of aluminum, pretty low resistance. I get very small thermal resistances for these conduction through these materials. So contact resistance, even though it's tiny, we looked up this value over here. Oh, where did it go? Oh, it's right here. Okay, but the conduction resistance for metals, for a slab of metal, is pretty small itself. So this contact resistance might be on the same order and is important to include. But if I have a layer of brick and a layer of wood, for these layers, unless I have super thin layers, but realistic layers, my thermal resistance for this is going to be so much bigger that this little contact resistance added on top of that thermal resistance is not going to show up. It won't make a difference. So if you think back to when you did these kinds of problems before, we very rarely had to worry about contact resistance. And that was because most often we're looking at materials that their thermal resistance is already so large. If we were looking at a thermal resistance, maybe we got a 1 out here due to contact resistance. It didn't have an effect. But if we have two slabs of metal, they might have resistances that are quite small themselves. And now the contact resistance is on the order of magnitude of the slab of metal itself. Okay. Hopefully my pictures, I think if you look back at your notes, you won't know why I drew this, but hopefully while we talked about it, it made sense. Another feature to talk about when we are in this resistance network section of the textbook is critical radius for thermal resistance. Okay. This only applies for cylindrical and spherical geometries. we never talk about a critical thickness if we are adding, changing thermal resistance of a wall section. If I drew a cylinder, and we are going to imagine that this is my chunk of material. So I'm looking at a cylindrical tube wall, inside radius and outer radius. And I'm going to have convection over this outer tube. If I looked for the thermal resistance due to conduction through this cylindrical wall, it looks like we've already talked about the radii, so I think you are imagining this. This is going to be thermal conductivity for the tube, and this is the length of the tube. This figure that is on the notes is for a particular case. I swiped this from the book. It shows the features, but I don't like you thinking that something particular happens at this r minus ri, this inner radius of 6. That's really for a particular problem. But the problem I want to talk about shows the same trends. So if I look at conduction, and I'm plotting this as I'm increasing R outside. So this is R outside as it gets bigger and bigger, R outside. If it grows in this direction, this curve is showing that I get a higher, larger and larger thermal resistance due to conduction. And I think that would make sense to you. You think about if I had this wall, it's made of copper, it's made of some plastic, whatever it is, as I put more and more material, I'm going to have a bigger resistance for heat trying to move through that wall. And if I think about convection on the outer surface, it's 1 over heat transfer coefficient and the surface area. And I'll expand surface area out into 2 pi. And I'll put an R outside and L. So those are my surface areas. So now if this R outside, let's make it keep getting bigger. So again, this is my R outside minus R inside as it gets bigger and bigger. Since surface area is in the denominator, the resistance due to convection is dropping off. So that's this curve. Okay. And because this is 2 resistances in series, we're adding them up. That's the next piece that this curve is showing, is that we've got this combination of these 2 resistance elements. So originally, I have no conduction resistance, and it's all convection. But at different places, I'm adding up this value, and I'm adding up this value. So I get up to this part of the curve. And because they are going in opposing directions, there is a place where I may have a minimum thermal resistance. So maybe now is where I should write my definition. Below, and this is for this particular case, R critical is where we hit the minimum. Okay. So below R crit, okay, and I'm sorry, as I look at this, I was going to keep going. Let's put a lowercase r for a radius. I don't like that capital R. To me, it looks like a thermal resistance. Okay, below R crit, adding material. To increase R outside will result in an overall smaller thermal resistance. Okay, so just to hit that one more time, and again, it's not always at this R minus, R outside minus R inside of 6 millimeters, but for each system, there's going to be a particular spot. And so if I think I would like to reduce my heat loss from a pipe, for example. So let's say I'm sitting here, this R location, and I think, well, I'll make the wall thicker. And that seems like a good plan. But if I'm below R critical, adding thickness, adding material to the wall, because it increases the surface area for convection, actually shows an overall drop. So I think it's an interesting feature to think about. Once I get past R critical, now when I add material, now I'm going in the direction I expect, that the resistance is going to result in a reduced rate of heat loss. I'm going to scroll back to a table that we've looked at previously. This note at the bottom says the critical radius of insulation is R crit is K over H for a cylinder and 2K over H for a sphere. So we don't use this a whole lot. It just happens to be in this table, and I thought I would mention. And you can see it has something to do with the behavior of the material, so thermal conductivity of the material and the heat transfer coefficient. This is a problem taken from your textbook, and I think it's a pretty good example, and we'll take a look at it. And my title here is Inputs Within Thermal Resistance Network. So normally, I think of those 4 rules for when you use thermal resistances. The rules are, it has to be one-dimensional conduction, steady state conduction, constant properties, and no volumetric heat generation. So I can't have, if I have a chunk of material and this has got volumetric heat generation going on in it, and maybe have another slab of material up here, I cannot write a thermal resistance element. Ooh, that was messy. Thermal resistance element across this one. But starting at this surface, as long as it follows all the other rules, I can use thermal resistance network across this other element, as long as it follows all those rules, no volumetric heat generation. Okay. This problem, we are going to use thermal resistance network, but we are going to handle having heat added at certain nodes in the resistance network. And what I still cannot, let's make a note, I cannot write a thermal resistance network equation across a node where I have heat addition, but I can write a summation at that node. This reminds me a little bit of electrical circuits class, because sometimes you worked all the way across a circuit. Sometimes you worked at a particular node. I wish I could remember the names of those two different equations, like compatibility and I don't know. But we are going to do this second case, way more common, at least for the undergraduate heat transfer class. We write resistance networks across the whole a whole system, and we say we can't handle it if we had a heat addition. But there is this other little technique that may be used. Okay, so I need to get you oriented to this problem. So what this says is that we have a solar panel, and it's made up of a glass layer, an adhesive layer, and a silicon layer. It has solar radiation coming in, and they tell us the amount, the flux that's coming in. And then they show this nice ray, and 7% gets reflected, so never even heats up the surface. 10% gets absorbed at the surface, and the remaining amount makes it to the silicon material and gets absorbed in that silicon layer. And then of that 83% of the solar irradiation, some amount of that gets converted to electricity, and some of it serves to heat up that silicon layer. They've already sketched this resistance network for us, and we are going to work with that. But maybe let's get a little bit oriented to this, and let me list the assumptions too, since I do not have a full given statement written out for you. Okay. We're looking at a steady state system. That needs to be true. One-dimensional heat transfer. We don't have an X shown in here, but just that you're thinking about through this material, things that are changing in the X direction. Constant properties. No contact resistances. Okay, this is the only one that I think you'd have to have some insight to think about this. We have this silicon layer, and they give us no thickness for that silicon layer. We got a thickness for the adhesive. We've got thickness for the glass. We're going to estimate that the silicon layer is thin enough so that there's no temperature variation across the silicon layer. Now, if we look at this resistance network, we have dots given here for the temperature nodes. So this temperature node down here, they're giving us TSI, and so we're thinking that's the temperature of the silicon. TG with the subscript G bottom means the lower temperature of the glass. So we went through a thermal resistance element of the adhesive. Now we got the bottom of the glass, and we got the top of the glass temperature node. And then two more temperatures off the top surface of this solar panel. We can have radiation to the surrounding temperature, which is given, and we can have convection to freeze-stream temperature, which is given. And they've got the pathways, the resistance elements for convection, and oh, here we have it, this radiation. There's a little H subscript R, and convection on the other side. Okay. The other piece that they've shown here is that at this top of the glass, they're saying 10% of G, the irradiation, and then to get it to a total amount of energy, they're multiplying by length times width, so the surface area is put into it's a energy addition to the top surface of the glass. And on this lower silicon surface, so they show solar energy coming in. They told us 10% got absorbed at the top. We handled that. 83% makes it to the silicon surface, silicon wafer surface, or the slice of silicon. Okay. The piece we haven't talked about yet is that they tell us the efficiency for converting this solar energy to electricity is eta. And we're going to use a particular value in there, but that 8 is there. So it says I've got solar energy coming into this node, but I have some of it leaving because I convert it to electricity. And the difference between those two is actually what heats up that silicon layer. We're going to set up this problem. And it takes a little bit of thought to think this through, but you know, we could pick different nodes that won't end up working, but I'm going to show you 2 nodes that give me a solvable system of equations. I want to start first with an energy balance on the bottom node, so the silicon surface. So I'm putting in 0.83. I put a little G subscript S, so that's my solar irradiation. And instead of carrying the L times W, I'm just going to call it an area, surface area. Okay. So this is my node, my temperature node for the silicon. Okay. I have, and I'm going to pick it in this direction, I have heat leaving that top surface. It has to pass through the adhesive and through the glass. And I'm going to call that Q top for right now, and we'll expand that out. And then I also have energy leaving, and again, that's the amount of electricity I produced. I want to write Q top, so heat transfer leaving the top of this node. And there's different ways you could do this. So again, you might write it down one way and see why there's a better way to do it. So I'm going to suggest we're going to write it as a temperature difference between the silicon node and the top of the glass. Okay. And I've just written the really basic equation that may stick with people to remember how these, you know, I want to have temperature difference on top. I want to have thermal resistances on the bottom. Okay. So if I'm working between those temperature nodes, the resistances I need are through the adhesive and through the glass. So I want to put this equation together. What I have coming in is and what I have leaving okay, I can already think of it. I haven't told you what we're trying to solve for in this problem. we don't know temperature of silicon, temperature at the bottom of the glass, temperature at the top of the glass. And our goal is really to solve for temperature of the silicon. I haven't provided all of the information, but let me put little checks over. We know, and this area is going to cancel on each of these, so I'm not going to worry about area. We know eta, we know this, we know. So the things we don't know are these two temperatures. Okay, but two temperatures in that single equation, I can't solve it. So the next thing we're going to do is try another energy balance on another node. And I'm going to pick the place where we have this, looking at this top of the glass temperature given.
Are we saying that the efficiency is 83% as well?
This eta?
Yes.
No, it is something. So really what this problem did is they allowed the eta to float. They'd say, if I had 25% efficiency, what would my temperature be? If I had 10% efficiency, what would the temperature of silicon be? But we're going to say we know it. We're going to guess it. It's an independent variable. We can pick what we have, and it's not 83%.
Okay, I was just curious where we're getting that from. Thank you.
Okay. Okay, yes, you're right. I haven't, a lot of things are given in this problem. And one of the things they didn't give was the efficiency, because they were looking at a whole range of efficiencies. But we're going to say we're going to pick a value in order to develop our solution.
So the 83 in the problem isn't the efficiency. That's something else.
Okay, I couldn't hear you.
I think my confusion came from the 83 in the problem isn't the 83 efficiency you mentioned. That's a whole separate thing. The efficiency is just the eta.
Yes, 83% is the fraction of solar energy that gets to the silicon.
Okay.
The eta,
okay.
Gotcha. Eta is how much of that you convert to electricity.
Okay, that makes more sense. Thank you.
Sure. So this is my top of the glass. And coming into that, and I'll scan up to the figure in just a minute, but I have what I've already defined as moving up that resistance network, Q top. I have 10% of solar radiation times area. And I have Q radiation and Q convection. So I'm going to scroll up for just a minute to look at our picture. So we're looking at this node now. And so I've got that, what I call Q top going into the node. We considered that 10% absorbed at the top. And here's my radiation and convection.
So the Q top you mentioned is the same through those bottom 3 nodes?
It is. So whatever leaves this node has to go through this guy. I don't have any heat addition, and it has to be what's going into that node.
Okay.
So we're going to put this equation together again. So that's going in. And then on the other side of the equation, I've got the 2 terms leaving. I'm going to write this the same way as we wrote it above. And I'm going to expand out radiation. Okay. If I went through and gave check marks to knowns and unknowns, again, we're given the flux. We know properties for these materials. I don't know either of these temperatures. I know emissivity. I don't know this temperature. I know that one. I know heat transfer coefficient. I don't know the top. I do know T infinity. The result is that I have these 2 equations. With unknown temperature of thick glass and temperature for silicon. And I can solve these for those 2 temperatures. I'm going to comment that it's not trivial to come up with the solution. I put it in ease because you can see I've got some temperatures to the 4th to deal with. And I think you guys have some other things that you may use, Wolfram alpha or alpha Wolfram. I never remember the direction. Some of you do solvers on your calculators. The result is oh, and I'll tell you, I did eta of 25%. So it was a lot of work setting up these nodal equations. But the bit that I wanted to talk about for a minute is that I am used to thinking about the fact that I cannot use thermoresistance concept when I've got heat addition. But I can as long as I appropriately account for it. And in that way, I can do energy balances at these nodes. And I can write the resistance element across a set of nodes as long as there's not heat addition across that node. Okay, so main point of that problem was I can do use the resistance element method. And a bit that you didn't get to see because I felt like I was so sure we'd end early, but then I talked too long. I showed on my notes, I wrote an equation at this node. It didn't do me any good. It didn't give me, it just added another equation with another unknown. So it ended up being more useful to go ahead and write a nodal equation at that top node. So just the idea that it may be, if you ran these all the time, you'd be really quick at it. But if you don't see them all the time, you may pick a node, not useful. We tried another node at the top, and it gave us the required unknowns that we needed to solve for. Okay, I actually have one more thing, and I'm not going to hit it today. We are out of time for today. So something new, parallel path method and isothermal plane. I'm going to end class for today, but I will stay on for a few minutes. Oh, and I'm going to apologize because